Hello and welcome to our presentation. I'm Sandipan from IIT Guwahati, and I'm happy to share our work resolving semantic confusions for improved zero-shot detection. In conventional object detection, the training images are passed through a feature extractor. We then look for possible regions with objects, and within these regions, we try to classify the object we are looking for and also simultaneously localize them within bounding boxes. However, annotating such bounding boxes for large-scale datasets are extremely time-consuming. Moreover, such supervised object detectors can only detect objects that are seen during training. Such models are susceptible to object appearance changes, and it is impossible to collect images for all the objects present in the world. Hence, such kind of detectors may not detect the rare objects present in nature. In zero-shot learning, we have visual idea about a scene class, combine it with some semantic idea like characteristics of an object, and we try to learn a visual semantic mapping. Using this mapping, we aim to achieve unseen class recognition and detection. The existing zero-shot detection approaches can be classified into the follows. The first one being improving alignment of visual semantic features, reducing background unseen confusion, learning from textual descriptions, utilizing data structures like graphs, and leveraging generating approaches. To explain semantic confusion, let's say we have all these objects and the visual features of all these objects are projected into the semantic space. Intuitively, we can see that semantically close objects tend to be similar in appearance and vice versa, and the same is reflected in their semantic vectors as well. One example can be seen from the MS COCO dataset, where the state-of-art method has wrongly detected the train as a bus. As a practical consequence, we can run into low average precisions, which can negatively impact our applications. In our approach, we have two steps. The first one being training a faster RCNN on scene class data, and next, synthesizing features while reducing semantic confusion. Let's look at them one by one. In step one, we have training images from scene objects only, which have ground truth annotations of bounding boxes. We pass them through a feature extractor, which is pre-trained on ImageNet after removing some overlapping classes according to existing literature's zero-shot criteria. Then we pass them through region proposal network, which looks for possible object regions. And finally, we have two pipelines. One is the bounding box regressor, which tries to localize, and the classifier, which tries to classify into one of n classes. In step two, we have a conditional GAN here, where we have two networks, the generator and the critic. The generator network takes two inputs, semantic vectors of seen unseen classes, as well as random nuts. The critic network will take object features from scene data as input. While training, the generator will try to generate object features, which will be sent to separate pipelines, which will show below. First, one classifier, which ensures that the generated object features are easily classified by a classifier. We also have a mode-seeking loss, LMS, which tries to diversify the object features of a particular class. Now, we have a mapper function, which gets input as visual features of some scene classes, such as kite, and it tries to map it to the semantic feature of kite. This mapper function is trained on the scene class data. Once trained, the trained visual semantic mapper is given the generated object feature as an input, and it tries to generate a semantic feature, which we try to have a cyclic consistency loss, which ensures that the generated object features correspond to their own semantics really well, and hence can be reconstructed. We also have a triplet module, which we'll be discussing in the next slide. Once trained, the generator can generate unseen features, which can be sent to the classifier of the faster RCNN, updating it for detecting and recognizing unseen classes. One of the main modules of our work is the triplet module, wherein in the generated visual feature space, we have an anchor of a particular class, and a positive match will be an object feature of the same class, a negative match will be an object feature of the different class. In such a way, we account for interclass dissimilarities using such a triplet loss, where the margin delta is not a fixed value, but a flexible margin, which is calculated according to the first and second order statistics of the semantic vectors of the seen and unseen classes. Hence, these triplets are strictly visual feature based, but semantic information also aids as a margin. Coming to the experiments, first data set is the MS-COCO data set with 65 seen and 15 unseen classes. The next data set is PASCAL-VOC with 16 seen and 4 unseen classes. The semantics we are taking from fast text. Evaluation metrics, the first one is the mean average precision, which is commonly used for object detection. The second one being recall at 100, which is recall value when only the top 100 detections are selected. We also have two separate detection settings. First one, where we have images containing only unseen objects, and the second one, which is the more difficult and more practical setting, the generalized setting, where test set has images containing both seen and unseen objects. Looking at the quantitative results for MAP on MS-COCO, you can see that we beat the existing state of art comprehensively, with the best results in red and second best in blue. The similar trend can be seen for recall at 100 also. Class-wise MAPs on unseen, we can see that the unseen classes are getting detected really well. Coming to Pascal dataset, our method performs comparably well with the state of art and is currently the second best to state of art, which is SUSE. You can also see that at different IU values, the recall at 100, we have comprehensively beaten all the existing state-of-the-art methods. In the qualitative results, we can see that in zero-shot as well as generalized zero-shot settings, we are getting really good results with a variety of correct detections. Even the small objects like the person inside the train is getting localized and correctly recognized. Comparing with the state of art, we can see that our results on the right are performing really well, reducing semantic confusion as compared to the state of art results. Similar trends can be seen in PASCAL-VOC, wherein comparing with the state of art, we can see that semantic confusion between semantically close classes like train and car are getting reduced and are getting resolved. TSNE plot of the generated features show that we have good separability between the classes. An evaluation study shows us that the effect of different loss components is really good, especially the triplet loss and the cyclic consistency loss are having the biggest impacts on our models. We also see that when we generate 250 unseen class features for every unseen class, we are getting the best results for both zero-shot and generalized zero-shot settings. Summarizing, we have the following contributions. We introduced the triplet loss, which accounts for interclass dissimilarity. We ensured that our generated features correspond to their own semantics via the cyclic consistency loss. And we address problems such as high false positive rate and misclassification of localized objects as a byproduct of resolving semantic confusion. While comparing the state of the art, we can see that we achieved a relative MAP gain of about 8% in zero-shot settings and about 10.5% in generalized zero-shot settings for MS-COCO, with comparable performance for Pascal. We have a better robustness against background clutter and occlusion. Moreover, as the TSNE plot showed us, we also have improved separability of the generated features, which is achieved between semantically similar classes. Our project repository can be found here. Thank you for watching. Hope you have a great day.